Analytical Chemistry 1, Lesson 49. We have seen how the chelating reaction between EDTA and a metal ion is structured to focus on the concentration of the fully deprotonated Y4- form of EDTA. Because EDTA is an acid, the way in which the 7 forms partition themselves shifts with changes in the pH of the solution. Because of this, the formation constant is conditional upon the pH of the solution. We structure the formation constant in terms of the total concentration of free EDTA. Now, this is the total concentration of EDTA in all 7 of its acid-base forms, from H6Y2+ down to Y4-. This is not the same as the formal EDTA concentration. It does not include EDTA that is complexed with any metal ions. Only free EDTA is included here. The alpha term, the fraction of the composition that is in the Y4- form, is dependent upon pH. If we now restrict our discussion to situations wherein the solution pH has been fixed with a buffer, we can move the alpha and combine it with the formation constant, forming the conditional formation constant, the formation constant that is conditional upon the pH. We label this conditional formation constant as K prime. Tables of formation constants are available for all the metal ions. The Y4- fractional composition at different values of pH is readily calculated, and in tables, we presented that table in the just previous lesson. By taking the two values, we can easily calculate a conditional formation constant at a given pH. Here's a table of values for 58 different metal ions. These are the formation constants and need to be combined with a fractional composition value for a particular pH. Here's the table of fractional composition values repeated again from the last lesson. Now, a couple of examples. What is the conditional formation constant for EDTA combined with the uranium 4+ ion at a pH of 7.5? From the tables, the log of the formation constant is 25.7. The formation constant is therefore 5.01 times 10 to the 25. From the table, the fractional composition of Y4- at a pH of 7.5 is 1.29 times 10 to the minus 3. Therefore, the conditional formation constant is the product of those two terms, 6.46 times 10 to the 22. And another. What is the conditional formation constant for EDTA combining with the sodium ion at a pH of 11? From the tables, the log of the formation constant is 1.86. The formation constant is, therefore, 72.4. This is so very much smaller than that for uranium. The uranium complex is much more stable. From the table, the fractional composition of Y4- at a pH of 11 is 0.810. This tells us that 81% of all free EDTA is present in the 4- form at this pH. Therefore, the conditional formation constant is the product of those two terms, 58.6. Even though the amount of EDTA available as Y4- is much smaller at the lower pH, the stability of the uranium complex greatly favors its formation compared to that with sodium. So how do we use these constants? Well, another example. Make up a solution that is formally 0.01 molar in magnesium Y2+. What is the concentration of free magnesium at a pH of 6 and at a pH of 10? Here's the K value for magnesium and the fractional composition for both pHs. From them, we can calculate the conditional formation constant at these two pH values. This is the equation for the conditional formation constant. For this problem, the dissociation of the added complex ion must produce equal amounts of EDTA and magnesium 2+, and that amount is subtracted from the formal complex concentration. This is just an ICE calculation. Solve the quadratic for x and find the concentration at the two pH values. The complex has dissociated considerably more at the lower, more acidic pH, more than 120 times greater dissociation. The lesson here is that a metal EDTA complex is less stable as the pH drops and the solution becomes more acidic. This is because protons start to compete with the metal ions for the ligand sites on the EDTA. Try one more. Make up a solution that is formally 0.01 molar in indium EDTA. What's the concentration of the indium EDTA complex at a pH of 6 and at a pH of 10? Here's the K value for the indium complex. Haha! Who cares about the pH adjustment? The complex will hardly dissociate at all. The concentration will remain at 0.01 molar. But if we were being asked about the free indium or free EDTA concentration, we could solve it as before. Here are the fractional composition values again, and the conditional formation constants. Using the same quadratic, we will get an indium ion concentration of 8.45 times 10 to the minus 12 molar at a pH of 6, while in the pH equals 10 solution, the concentration will be 6.45 times 10 to the minus 14 molar. And as we expected, it doesn't make a measurable dent in the concentration of the metal complex. The stability of a metal EDTA complex depends on both the nature of the interaction with the EDTA and upon the solution pH.